Hello, everybody. I hope after today's keynote, you're as excited about PyTorch 1.0 as we are. Today, I'm going to tell you how we use PyTorch 1.0 and other tools to take AI research into production at Facebook. So first, I'm going to talk about AI research and why it's so important to everything that we do at Facebook. Then I'm going to talk about the open source tools that we have available for you to use to develop AI. I'm going to talk about how we take these tools and we use them to take AI from our research labs into production. And then I'm going to talk about what tools we're developing for the future and how we think about making new AI tools. So AI research is an important part of everything we do at Facebook. AI is a big part of how we're thinking about inventing the future on our platform. And research is how we create that technology that's going to be, the future of Facebook. So at Facebook, we're focused on advancing the state of the art of AI, not only for Facebook, but also for the entire world. We want to make sure that we are advancing the state of the art for the field, for anybody that's using AI in any industry, for any application. So we do this in the open, we publish, we give our researchers freedom to work on whatever problems they think are important in AI. And we create a center of excellence built with the world's best people focused on the hardest problems in AI. So we started FAIR, Facebook AI Research, in 2013 with Jan LeCun. We founded a lab in New York and Menlo Park. Since then, we've opened several other locations, and we continue to expand so that we can tackle more challenging AI problems. The lab has more than 130 members composed of people from 20 different countries and a mix of researchers, engineers, students, all focused on different problems in AI. We work on the whole spectrum of AI, everything from vision to reinforcement learning, natural language processing, optimization, and we're committed to doing this in the open. Since 2016, we've published more than 150 papers, which have had enormous impact in the field. For example, they've been cited more than 7,000 times. We open source a lot of our software that we use to make this AI and also the models themselves. We have dozens of projects available on GitHub, and they have been starred more than 30,000 times. So people are really using these tools. We've also won multiple Best Paper awards at some of the top AI conferences. And in addition to having a big impact externally with our work, it also has a big impact inside of Facebook. We use a large variety of different types of machine learning models in our application. Here's an example of a few, but there are many more. And this AI, these models power some pretty amazing experiences on the platform. For example, there are millions of people on the platform that have some sort of visual impairment, which makes it difficult for them to interact with photos and videos and all sorts of other visual content that their friends and family have uploaded. And so we use AI to analyze what is in the picture and actually describe it to people so that they can understand what their friends are posting. So this enables anybody then to have the full experience on Facebook. There are also many different languages spoken on the platform, and we want people to understand posts and comments no matter the language that they're in. And so a year ago, we had a phrase-based version of translation, and it didn't always have the most natural translations. For example, we might end up with something like this. And while that's useful, there's a lot of cases then where it just didn't really create a great experience. However, we developed a new model based on neural networks in FAIR, and we were able to put that into production. And now we have translations that look like this, that really work, that are natural. And this enables people to connect on the platform no matter what language they speak. And the impact of this is enormous. We have more than 45 languages on our platform that we can support with this translation. That results in more than 2,000 language pairs. And this powers almost 6 billion translations a day on the platform. Another really interesting application is face recognition. Late last year, we launched a feature called Photo Review that allows people to, we use AI to help people protect their privacy and protect their image on Facebook. So if you're like me, you may have had a situation where you went to a party or an event, and there was a bunch of group photos taken, and it was taken by a friend of a friend. And so they put it up on Facebook, and you would love to be able to comment and see the photo and participate in the conversation, but since it wasn't your friend posting, you have no idea that your picture is up there. So with Photo Review, what we do is now we use AI to analyze your friends of friends' photos and recognize that you're in them and notify you, which means now you can tag yourself, you can comment, and engage in the discussion that's happening around this great group photo. You also can ask to have it taken down if there's some sort of issue. So now you can feel comfortable that you know when your image is on Facebook. This also powers another really important feature. We found in user research that in other countries, women in particular were very concerned about having their profile picture up in case somebody might copy it and then make a fake account and damage their reputation. So we use the same face recognition technology to notify you if your image is being used as a profile picture anywhere. And then we can immediately shut down that account. So now you can feel confident that your image is representing you alone. And this makes people much more comfortable to be their authentic selves on our platform. Another really important issue is how we talk to each other on Facebook. Spam and hate speech and bullying and other content and comments like that make people much less likely to want to share or engage and really ruin the experience when you post something great. So let's say I've posted a picture like this, okay? And if I look, right, I have, one really great comment from a friend and another thing from a spammer, and that ruins my experience in terms of interacting with the picture. And so we use natural language processing to analyze every single comment and then remove comments that are spam or hate speech, bullying, copyright infringement, all sorts of things. And so now we can make sure that the comments we have on Facebook are the comments that you really want. So all of this, so AI also powers many, many other experiences. This is just a sample. But all of this is built on tools. Tools are an important part of how we develop technology like this and future technology. And so I'm going to talk about the tools that we use. And lucky for you, we open source all of them. So it's a great chance for you to be able to do the same thing in your companies. So at Facebook, we open source tools at every single level of the stack, starting with hardware. We have open source hardware. We have compilers and optimizers that allow you to get the best experience on that hardware. We have state-of-the-art frameworks that allow you to build models, train them, and execute them on top of cutting-edge hardware. We have libraries built on top of those frameworks that capture the latest new AI advances, great models, and other research. We have pre-trained models built on open data, built on Facebook data, all sorts of different data sets that you can use and put in your applications directly. And we also open source data sets so that others can learn how to build better models from our data. And together, this enables us to really think about the whole AI picture and develop great tools thinking about every single part of the stack. So I'm going to talk a little bit about each one of these, starting with hardware. So Facebook actually open sources hardware, which is very interesting. We started doing this in 2010 with the Open Compute project. And there's two ways you can really think about designing hardware. One way is you have a global shared pool. You have one hardware design that every application runs on. And this is great because it's really simple. Everything runs on the same thing. It's easy to manage. You only have to have one design. The problem is different applications have different needs. And so this can be a challenge in terms of getting the efficiency that we really want at scale. The other way to go is to have customized dedicated hardware for every single application. So in this case, you could have maximum efficiency. But the challenge here is that it's very difficult to manage, it can be complex, and also you don't have the ability to reuse resources. If one application needs more and it's out of its hardware, well, it may not be able to run on the other one that was designed. And so at Facebook, we actually take an approach that's between these two. We take a small number of major services that have different resource requirements, and we make a design tailored to each one of those. Then we map all of our applications onto those couple pieces of hardware so that we can get a balance of, great efficiency, but also something that's elastic and easy to manage. So I'm going to talk about some of these different designs. This is a picture of Big Sur, which is some of our new AI hardware. But first, I'm going to start by talking about Twin Lakes. Twin Lakes is our hardware design for our serverless applications. So it's designed specifically for applications that have small amounts of computation. They have high data access and high I/O. It's basically optimized for throughput. We use a small form factor and 4 CPUs in a single socket so that we can get the maximum number of requests going through this, so that we can serve many, many requests in our web tier. We also have Tioga Pass, which is for more powerful CPU computation. It has 2 SSDs, lots of memory, and 2 sockets. So this is where we put our really compute-heavy or memory-intensive workloads. We also have Bryce Canyon, and this is really important for AI. Bryce Canyon is focused on storing data for us and I/O to get that data in and out. And since AI is built on top of data, Bryce Canyon is an important part of that story for us, getting all of that Facebook data in to train our models. Finally, we started experimenting a few years ago in 2013 with hardware specifically for training machine learning. So Bobcat was an off-the-shelf starting point that we used. We learned from that, and then we started designing our own GPU racks. So we released Big Sur, and we have just recently released Big Basin, which uses just a bunch of GPUs design using NVIDIA's latest Voltas, powered by a Tioga Pass head node. So this enables us to do machine learning training at scale. So that's our hardware suite, and now I'm going to talk about our compilers and optimizers that we have available that enable us to get great performance on that hardware. So one of them we just released today. It's now open source, so you can go use it. It's called Glow. And Glow is a compiler toolkit specifically built for ML accelerators. So the idea is if there's new machine learning acceleration hardware, it's easy to use this compiler to automatically get the important optimization so you get maximum performance on that hardware. So it has built-in high-level domain-specific optimizations, low-level memory management optimizations, and many other types of optimization. It also has quantization of floating point models to integer, and it's integrated with Onyx. So this is just one of the many tools we have in this space that's available. It's an early stage research project, so definitely try it out and get involved, and we will be continuing to work on it out in the open. On top of our compilers and optimizers, we have frameworks. And frameworks are the piece that we use to build our models and train them and run them for inference. At Facebook, we use PyTorch 1.0 for our frameworks, and PyTorch 1.0 takes the best of PyTorch, Onyx, and Caffe2 combined. So we take the flexible performance of PyTorch with the completely open interoperability of Onyx and the high performance, extreme optimization, extreme scale of the Caffe2 backend, and we put them together in a single framework. So now you get the benefit of all of these together with PyTorch 1.0. I'm going to talk more about how we use this later. But in the meantime, I'm going to talk a little bit about some of the things we've built on top of PyTorch 1.0 that we've made available to you. So we have libraries, models, and data sets on top of this to make it easier for you to take advantage of the things we've already built. So we're building a new PyTorch ecosystem that has all of these tools available for many different applications, whether that's vision or reasoning or language, speech, or just general purpose tools. We're putting them out there in the PyTorch ecosystem so that you can use them. So one example is Detectron. Detectron is a vision library that we use to do state-of-the-art object detection research. We've built in many of our existing technologies that you've seen showcased here at F8. And we also have more than 50 pre-trained models for you to download and use in your application. Let's see. Oops. So anyway, open source, as I said, this is just a small sample of what we've open sourced. We have many, many more that I can't talk about today, and many more that are on this slide, and we'll be continuing to open source things at every level. So you can go to facebook.ai/developers to learn more about the latest things we've released. And every single one of these components that we've designed is using an Unframework philosophy, which means rather than designing one monolithic tool chain, we're focusing on making important components that you can put together as you need. So you can customize them and configure them into any combination. Because every AI application is different, and people need different tools. So this enables us to put together the combination that's right for that particular research and that particular production scenario. So if we put this all together, let's look at what a machine learning execution flow looks like. So we start with data, and we transfer data into features. And then we design models, and we train them based on that data. And we evaluate how well the model is doing. And we go around and around offline until we find a model that we really like. And once we have a model that's performing well, then we put it online in our applications, and we do inference so that we can actually use the model. And so if we put together all of the tools I've been talking about, we have open data sets and libraries that allow you to use our data or generate great features for your models. Then we use PyTorch 1.0 to train and evaluate. And then once we have a model, we can take it into production with PyTorch 1.0. And we've also released tons of pre-trained models that you can run in PyTorch or your favorite framework for inference. On top of that, we have all of the great hardware I was just talking about. So you can use the Bryce Canyon design to store data. We use Big Basin for training, and we use that Twin Lakes to run inference in our applications. So let's talk about how we use all of these tools to take our AI research and put it into production. So when I'm in research, we're thinking about how do we develop new models, new algorithms, new methods that allow us to better capture the patterns in data and replay them in applications. Once we have a model that we like and we think is ready for real applications, then we want to think about how do we scale this? How do we make sure that we can train on Facebook data at massive scale, like the 3.5 billion image model you heard about earlier today? After that, we don't stop there. Lots of our models actually run on the phone so that you can get the best, so users can get the best, most responsive models in their applications. So when we thought about going, so many cases when we were taking research to production at Facebook actually involved needing to use 3 different tools. We would start by developing in PyTorch because of its flexible front end, which I'll talk more about. Then we would transfer models with Onyx, and we would go take them to Caffe2 for production at Facebook. So the end result was something that looked like this, where you'd start with one tool and transfer, and you'd need to use a third tool. And so with PyTorch 1.0, we're bringing all of these under the same tools. So you no longer have to transfer between 3 tools to take research to production. We're still using the Unframework approach here, so all of the components are on the inside, and so you can still customize them as you need, but it'll be a much more seamless experience to go between them. Also, Onyx is still a big part of this. It's native inside of PyTorch, and we can use it both to optimize our hardware runtimes, and also enable you to export to other tools that you need to. So let's get into how does this really work. Let's think about research. So as I mentioned, in research, we're focused on developing new models. And so it turns out there's actually 2 ways to do this that are being used right now. One of them is called an imperative technique, and the other one is declarative. And let's talk a little bit more about what that looks like. So until PyTorch came out last year, most of the common frameworks use a declarative approach, or also called a computational graph approach. And the idea with this is that you're going to declare your model as a graph. And you're going to compile the graph, and then we can run it repeatedly in a VM. So it looks something like this. So I declare my model. Here are my placeholder variables, inputs and outputs for my graph. And then I describe my model as a graph of mathematical functions. Then I compile the model, and I run it in a session in a Turing-complete separate virtual machine. And there's a lot to like about this approach. It's really easy to optimize. We can do amazing, because the graph is fully represented, we can do very interesting graph transformations and operator fusion. We can do things like reuse memory and all sorts of other state-of-the-art optimizations. The graph can also be serialized for production deployment on hardware runtimes or on mobile or any of the other places you would want to take it. The problem with this is it's a very non-intuitive programming model. Most of us were taught to program in a linear model, and if you're like me, maybe you don't naturally think in graphs. And so it takes a lot longer to write a graph program. The other challenge is it's not as expressive. If your model can't be represented in a graph, it's going to be difficult to get into this type of framework. The other challenge is the framework is difficult to design and maintain. It needs its own virtual machine, its own debugging tools, and its own compilers. So we have to basically make a separate computing stack for the framework, which takes a lot of time and is difficult to keep up to date. The other approach that people use are called imperative toolkits, and this is what PyTorch was designed to be from the beginning. And the idea with an imperative framework is that there is no graph particularly expressed. Instead, we're expressing models as a program. And so you just write down your computation, and it's as simple as that. Then you run your computation, and that is your model. There's no separate execution engine. It just runs in the Python execution engine, so we don't need to develop our own. And you can also use all of the latest great Python. You can use all of the great Python tools that like print statements and other great debugging tools. So this approach has a much more natural expressive programming model. We can put dynamic graphs in here. We can put other sorts of any kind of new AI research that people have thought of. And you have the ability to use the whole Python ecosystem. And it's much easier to debug because it's more natural and because of the ability to use existing debugging tools. The challenge with this approach is it's difficult to optimize. Because there is no graph, we cannot perform a lot of these graph transformations easily. And also, you're rebuilding the graph or the program every single time. So we're not compiling it and then just running it over and over again. It's recompiling every time. So the overhead can be significant, which matters when we're thinking about putting it in production. So what we're trying to do with PyTorch 1.0 is bridge these two worlds. We want to get the expressive, productive, flexible programming model of the imperatives and bring it together with the optimization and the runtime performance that we can get with a declarative framework. So let's look at how this works. So in PyTorch, if we had a program that looks like this, a simple program, what it produces looks like the graph on the right. And so if we were ready to take that into production, what we would do is we would export it in Onyx. And I know you've heard a lot about Onyx today, and we're going to talk a lot more about it in the next session. But for right now, what you need to know is that it's a way to represent machine learning models that we can use to transfer between frameworks. So we take our program and we add a simple Onyx export statement. And this tells PyTorch that we want to transform this program into a graph and we want to represent it as an Onyx model. And now, once we have this Onyx model, we can take it to Cafe 2 and put it in production. The challenge with this is there can be models that are difficult to export. For example, if we have control flow, then the model might not come out right. And so what we're doing in PyTorch 1.0 is we are actually expanding Onyx and PyTorch to be able to cover some of these more complex cases like control flow. And we're also building it into the front end. So rather than having to do a full export and go to another tool, you're going to be able to add annotations like this that tell the program, this module, we want it to be optimized for production. And so that will all be inside of PyTorch. No need to export and start another tool. The capabilities of PyTorch and Onyx and Cafe 2 will be all there, but it's Onyx on the inside that we're using to do this translation. So once we have that model in our production-ready Onyx format inside of the framework or externally, then we need to think about how are we going to train it at scale on production data. So at Facebook, we built Cafe 2 to be our production framework. It's production quality robustness. It has first-class distributed support. It works across many different types of platform, and it has incredible tools for deploying on mobile. And as you heard earlier today, this has huge impact at Facebook. It runs on more than 1 billion phones worldwide, and it serves 200 trillion translations a day. So it's incredibly important in everything that we do. So if we think about what are we trying to do when we want to do AI at scale? So one of the challenges is models get better when you use more data. So we're always driving to be able to train on more data at larger scales. Second, we want to take advantage of the great new hardware designs that are happening in research, happening in startups. And so we want to take advantage of the latest, faster compute so that we can move faster when we're training. And we want to use new algorithms which might be larger or more complex. And so putting this all together, we want to be able to leverage the most data possible as quickly as possible with advanced models. And to do this, we need to do distributed training. So if we look at a traditional HPC application with a MapReduce style computation, it's embarrassingly parallel. There is typically no dependency between shards and maybe very little communication between them as well. And it's often I/O bound. So it's very easy to parallelize. I can split the computation in several different chunks, maybe do a small amount of communication at the end to compute the result, and I'm set. Unfortunately, machine learning doesn't work like that. We have many different iterations with dependencies between iterations, which makes this much more challenging. So we have strong communication. So the way this works is we input a batch and we do the predictions and we compare the actual output to the expected output. And then we compute gradients and we update our parameters every single step. And the amount of computation here can be extremely high. In some models, we're needing to transfer 25 million parameters each iteration. And then we need to repeat this many times with transferring those parameters between the iterations. And so the way we distribute is we actually do distributed training in each iteration. So if we look at how this works, if I have a 3-layer network, if I was running it serially, it would look like this. So I would run my forward passes, then I would run the 3 backward passes, and then I would run an update function to get those new values, and then I would repeat. So if I want to do distributed training, I need to add a reduction step that allows me to accumulate the gradients that were computed in the backward passes and update. So if I want to run on 2 GPUs, then what I'm going to do is I will run the forward and backward passes in parallel. Then when we reach the reduction step, we're going to block, we're going to wait for both GPUs to finish, and then we're going to fetch and accumulate the gradients from the other GPU. Then we can run the update function in parallel. However, we can actually go farther than this. We don't need to wait for all of the backward passes to compute before we start doing the updates. So as soon as the 3rd layer backward pass is finished, we can start doing the reduction for that layer. And so we can actually run these in parallel and get higher performance. And so these techniques are already built into Caffe 2 so that the framework will actually automatically optimize the dependencies and run everything as much in parallel as it can. So you don't need to worry about any of this. And the impact can be significant. So here is us running ResNet 50 and some other common models on a NVIDIA DX1. And so we're actually seeing a 7x improvement in performance running on 8 GPUs. So almost linear performance, which means if we have more hardware, we can train that much faster, which is really important when you're actually looking at doing this at scale. So object detection is an important technology that we use in many different places on the platform. And so we need to train models for image detection at scale. So let's look at how this works with ImageNet, which is a common benchmark that's used in the community to train these models. So let's say I'm going to train my standard ImageNet everyday, cat detector. Then I'm going to need 8 gigaflops per image that I want to train, and there's 1.2 million images. And I need to run over each of these images 100 times to train a model. The result is an exaflop of computation, which is significant. So if we look at how long this is going to take, if we were doing this for ResNet 50 on a Tesla, NVIDIA Tesla P100, then we can train about 230 images a second. And as I mentioned, we need to run through them 100 times. And we have 1.2 million images, which means it's going to take 6 days to train just our basic standard image detection model. So that's a long time, particularly if we're using this technology to catch bad behavior on the platform or other things like that. We need models that are fresh and up to date and represent what's going on now. Again, whether that's some new attack or the latest hashtag, we want that in our models. And so what we did is we started a research project focused on how could we get even more distributed and get the best performance. So we scaled up our input batch size to about 8,000, and then we trained on 256 GPUs in a single training run. The result was a computational pattern that looks something like this. And with all of that technology put together, we were able to bring our training time down from 6 days to a single hour. And that greatly increases our ability to keep our models fresh. The great thing is that all of this technology is open source, as I've talked about, all the way down to the hardware, and the paper is published. So you can go and recreate these same techniques for your workload on your platform, or you can use our tools where it's built in. So once we've trained our models at scale, then we want to look at how do we take them farther? How do we take them out of the data center and get them onto the phones in the hands of people? And why do we want to do this? There's quite a few different reasons. If the model's on the phone, we don't need to send as much data to the cloud, which means this is more private for people, the models are also more responsive, and it's generally just a better user experience. So Café was designed with mobile built in from the beginning. So we call the mobile piece Café to Go, and this will be part of PyTorch 1.0 when it's released. And this enables pretty cool experiences. This is a key point detection model running on the phone in real time, where it can be analyzing through your camera and finding the key points in a video. And this enables us to create some pretty cool effects. So the challenge with running on mobile is the ecosystem is very fragmented. There's more than 20 different chipset vendors and 25 different CPU microarchitectures, 15 different GPU architectures, 2 major operating systems, 3 different graphics APIs, and 2 different compute APIs. And obviously, we need the models to run well on every combination of these, which can be very challenging. Luckily for you, we built all of this into Café 2 so that you don't have to deal with this fragmentation. Café to Go will automatically optimize for the combination of the platform that the model is running on. The end result is 5 different mobile device backends. Some of them we built custom. Others are built with our hardware partners and then leveraged inside of Café to Go. Café to Go also contains many optimizations that allow us to take the model to extreme size and performance on the phone. So we support floating point 32, we support FP16, int8, we have the ability to compress models, to quantize models, and to generally also trade off speed and accuracy, or speed with accuracy, so that you can find the combination that's right that will work really well on the phone. And so this is how we put this together. And the end result is that we have faster inference, no fragmentation, and we can put compressed models on the phone, which are really powerful. And so this is how we take research from PyTorch and scale it up and then put it into production and all the way into the phone with Café to Go. And all of this will be available in PyTorch 1.0. So let's talk a little bit about the future. What are we developing for the next generation of AI? So we will continue to be developing open source tools at every single level of the stack. And as new innovations come out, we will be trying to make the best tools to support that type of AI. We're deeply committed to making sure that all tools are hackable. There's lots of AI research that nobody's ever thought of yet. And if you're trying to do something new, the tools might not be designed to support it. And so it's important that you can go in and customize and change the tools to support whatever you're trying to do in research. And this has been incredibly important for us as we're developing it. So all of our components will continue to be easy to modify and open. And in addition to that, you can configure them in any combination that's right for you, so that whatever is the best thing for your researchers or the needs of your production platform, you can use the combination of tools that you need. Of course, we will have PyTorch 1.0 coming soon. We're developing it all in the open, so you can go to GitHub right now and see what we're doing. A lot of what's happening in PyTorch 1.0 is still open research, and it's an experiment. So you can see how we're trying to develop what the best tools for AI. I'm also very excited to announce that AWS and Microsoft have both agreed to support PyTorch in their cloud and developer tools offerings. So AWS will have it available in the DL AMI, and Microsoft is going to have it in Azure ML and the data science VMs. So you'll be able to go to the cloud of your choice and use all of these great tools easily. So I hope that you're as excited as we are about the coming of PyTorch 1.0. As I said, we're doing it all in the open, so we hope that you'll come and check it out, get involved, use it, give feedback. And we hope that this helps all of us create better AI to transform people's lives. So thank you very much.